Welcome to the 15th lecture on digital simulation. In this video, we will try to solve a problem given in the model question paper provided in the syllabus. So here I have copied the question here. So we have to solve a differential equation given by dx by dt is equal to minus half x minus 6t into e to the power minus t by 2 in the time span 0 to 20 with the initial condition x of 0 equal to 3. For two different step sizes 0.01 and 0.05 using two techniques, trapezoidal technique and forward Euler method. And we have to compare the solution with the analytical solution. Analytical solution is provided in the question itself, that is 2 minus 3t square e to the power minus t by 2. This is the analytical solution, and we have to calculate the global error at the final value. So let us rewrite the differential equation here. So dx by dt equal to this. This is the differential equation, and first we will try to solve this problem using forward Euler technique. So in the general expression for forward Euler technique, we know x of k plus 1 at t is equal to tk plus 1. At k plus 1th instant, value of x is given by value of x at kth instant xk plus the function evaluated at xk tk multiplied by step size h. So this is the general expression in forward Euler method. This we have seen in the previous videos. So here f of xk tk is the right hand side of this differential equation. This is the function f. So here you put x equal to xk and t is equal to tk. So this is the final expression for x of k plus 1. So here by substituting the value of x of 0 and t of 0, you will get x of 1. Then using x of 1 and t of 1, you can get x of 2 like that. Then let us look at the trapezoidal method. So in trapezoidal method, the k plus 1th value xk plus 1 is equal to xk plus h by 2 into function value at xk tk plus function value at xk plus 1 tk plus 1. So the function value at xk comma tk is nothing but that right hand side of the differential equation with x replaced by xk and t replaced by tk. Similarly, f of xk plus 1 comma tk plus 1 is just replace the x by xk plus 1 and t by tk plus 1 on the right hand side of the differential equation. And now by simplification, we will get this expression. This is the expression for xk plus 1. So here one important observation is both on the left hand side as well as on the right hand side, we have xk plus 1. So we have to group the terms of xk plus 1 and write an expression for xk plus 1. So if you collect the terms of xk plus 1 to the left hand side and divide this both whole equation by 1 plus 0.25h, we will get the final expression for xk plus 1 in terms of xk, tk and tk plus 1 and step size h. Okay, so these are the procedure or equations in Euler method, forward Euler method and trapezoidal rule. Now if you solve this problem using forward Euler method using MATLAB, this is the plot of solution obtained by forward Euler method. So the forward Euler method is solution obtained using forward Euler method is shown by red color, and solution obtained by exact solution. The exact solution is plotted in blue color. So this is the exact solution. In trapezoidal method also we will get the same result. This is for h is equal to 0.01. Now for h is equal to 0.05, similarly we can get the solution. So in both the values, both the step sizes h equal to 0.01 and h equal to 0.05, both the forward Euler and trapezoidal method gives a stable result. Okay, now let me show how I have solved it using MATLAB. So in MATLAB, you can type a function like this. So I am not going into the details of how to write this code. This we will study in detail in the fifth module. So initially this clear all will clear all the variables in the workspace. Then close all will close all the figure windows which are opened, and CLC will clear the command window. Then t is the t variable. Initial value of t is 0, so t of 1 equal to 0 and x of 1 equal to 3. This is the initialization, initial condition. Then we need to simulate the system, solve the system up to t equal to 20. So t end is taken as 20, and the step size is we can use either 0.01 or 0.05. So here I have entered 0.05. Then how many number of steps are there? That is time span divided by step size, t end by h. That value is equal to m. Now we can use a variable k for iterating this forward Euler equation in a loop, in a for loop. So this for loop runs from k equal to 1 to m minus 1. Then tk plus 1 is nothing but tk plus h, and xk plus 1 is just the equation that you have derived for xk plus 1 that you can substitute here. This expression using forward Euler method, the expression using forward Euler method. This is the expression 1 minus 0.5 h into xk minus 6h into tk into e to the power minus tk by 2. This you can substitute here. Then close the loop, end the loop. Then we can plot both the result x and the exact solution. So how to write these steps I will explain in the fifth module. So if you run this program, you will get the plot of this. Red line will give you the first plot, that is t versus x. X is the numerical solution or forward Euler solution, and the second blue color line shows the exact solution. We can add legend, x label, y label, title to the graph. All these things we can add. This I will show later. Similarly, you can write a similar code for the trapezoidal technique. Only difference will be in this step. To evaluate this xk plus 1 in the trapezoidal technique, the expression is quite lengthy. Okay, this is the expression in trapezoidal technique. So I have named this numerator as a and denominator as b, and then I have defined a and b here. A and b are defined here. Then x of k plus 1 is a by b. Only difference is there in evaluation of x of k plus 1. And if you simulate it, you will get the plot. So this is how we can solve a problem in using forward Euler method and the trapezoidal method. Now the global error at t is equal to 20 can be calculated by calculating x of t is equal to, from x of 0 on t is equal to 0, the value of x is x of 0. Like that, at t equal to 20 we will get the numerical solution. Then from that subtract the exact value of x at t equal to 20. The exact solution is given in the question itself, that is 2 minus 3t square into e to the power minus t by 2. So if you put t equal to 20 in this exact solution, you will get the value of x of t, x cap of t, that is the exact value of x at t equal to 20. Then the numerical value, so obtained numerical solution at t equal to 20 also can be found out from the program. Then if you take the difference, you will get the global error. Okay. So this is how we can solve a differential equation using forward Euler and trapezoidal method. Thank you.